Let's talk about magnetic sensors. So magnetic sensors allow you to sense the effect of a magnetic field. But before I get into the details of how that works, let's just show a demonstration of some magnetic sensors that you might have handy already. So this is just a simple laptop. It's a Chromebook, but that doesn't matter. Let's first look around for magnets on this device. So here I've just got a screwdriver. Any piece of steel or whatever will probably work for this. So basically I'm just going to pass this screwdriver around the edges of the frame of the laptop, and I can feel a tug when there's a magnet. So here's one right there. Let's keep going. There's another one. So there's a magnet here and here. Now let's keep going. Oh, and there's one right there. I'm also going to pass it around here. There's another magnet right there. And, there's one right there. So I'm going to guess from this that the magnets up here and the magnets up here are just there to keep the laptop closed, the lid closed when you close it. But there's another magnet here, and notice what happened when I passed that piece of steel there. I think this is slightly magnetic. There's basically, I think, a sensor right here on the side of the laptop that corresponds with this magnet, and that magnet and sensor combination tells the laptop when the lid is closed, and it says, hey, go to sleep. It tells the laptop basically when to sleep. So let's try and trigger that artificially. I have here a simple ceramic magnet that you might use on your refrigerator. It's a fairly weak magnet. Word of caution, really strong magnets and electronics usually don't go together that well, so I wouldn't recommend passing strong magnets around your laptop. Bad things might happen. So this is a pretty weak magnet. So we're just going to basically put this magnet over here close to the sensor location. Oh, there we go. So basically when I put that magnet close to that sensor location, it turns the screen off because it thinks the laptop lid is closed. Now let's pull that magnet away and see if it wakes back up. Yep, there you go. See, it thinks the lid is open again. So there you go. There's a sensor right here. I don't know what type of sensor, but I know that it can sense magnetic fields. So there's an application for magnetic sensors. All right, let's talk about the first type of magnetic sensor. So that is a reed switch. So this is a very simple device. It's this little tube here. So basically what it is a glass encapsulated, so it's basically a tiny glass tube with two metal leaves inside of it. And those metal leaves will move when there's a magnetic field present. And basically they'll close like a switch when a magnetic field is present. When there's no magnetic field, those leaves will be separated, so it'll be like an open circuit. So it's basically just like a push button, but the button you push is a magnet. So you'll notice there's two terminals. They're non-polar. Doesn't matter whether you hook up positive or ground to either side. That'll work fine, just like a switch. So this is just a fairly weak kitchen, like fridge magnet, ceramic magnet. I have the reed switch hooked up to an LED over here, and then 5 volts on the other side, and then the LED is hooked up to ground on the other side. So when I get the magnet close, you'll see the LED lights. When I pull it away, it turns off. Simple. Okay, so what are the positives and negatives of this sensor? So the positives are it's cheap, it's simple, It doesn't require power. It works just like a switch, no matter if it has power or not. Downsides are it's fairly fragile. It's a glass tube. It's easily broken. They do have plastic versions that are a little bit more expensive, that are more robust. So that solves that problem. But the biggest problem is it is a mechanical switch. So if you have an application where it's going to be opening and closing frequently, like if you're measuring rotations of a motor or revolutions of a motor, well, that might be opening and closing this switch thousands of times a second, or a minute, maybe. And basically that's going to wear that switch out in minutes or hours. So you want to use a different sensor for something that's going to be rapidly opening and closing. But for something, these are used commonly in door sensors. So, you know, when you open the front door to your house, if you want to sense that, often there'll be a magnet in the door and one of these sensors in the door frame. It is perfect for that because you're not opening and closing your door 1,000 times a minute. All right, the next set of sensors we're going to look at are called Hall effect sensors. So I have one here plugged into the breadboard. These differ from the reed switches that I previously showed in that they're solid state devices. What that means is that there are no mechanical parts that are moving when a magnetic field affects the sensor. So that makes these more useful for applications where the magnetic field is changing rapidly, like monitoring motor position and things of that nature that might be changing, 1,000 times a minute. This particular Hall effect sensor is actually what's called a linear Hall effect sensor or ratiometric Hall effect sensor, and what that really means is just that it outputs an analog voltage. So that's another feature that these sensors have over reed switches, is that they can actually measure the strength of the magnetic field rather than just giving you an on or off kind of output. So let's take a look at this. So again, I'm using kind of my little weak ceramic fridge magnet, and hopefully you can see the multimeter reading. As I get closer and closer, it was starting, the voltage started off around 2.5 volts, and it keeps getting lower and lower as I get close to it. And you might be asking, why is the sensor reading 2.5 volts from a 5 volt supply? Well, the reason is because this sensor can actually tell the difference. So I flipped my magnet around, and now you'll see the voltage is getting higher. Now it's up around 3 volts. So the point of that is that it can tell the difference between a north and south pole of a magnet and tell you the strength. So this is a fairly weak magnet, so it's not getting it anywhere near 0 or 5 volts. A stronger, like rare earth magnet might. And it's also worth noting that you see the range of this is not very long. We're talking about an inch or so. A stronger magnet might give you a larger range than that, but we're definitely talking like inches and centimeters, not feet, as far as range. The downside of these types of sensors are that, as you may be able to see here, there's actually 3 terminals. These sensors are actually powered. So I have to supply 5 volts ground, and then there's an output voltage, which is what my multimeter is hooked up to. So that's 3 wires instead of 2 if you're counting from the reed switches. So that's a downside. They're also more expensive than the reed switches, as you can imagine. So they're not that expensive, but just more expensive than the reed switches. So these sensors are useful where you want to actually measure the position of something. So you could have a magnet on the end of an adjustment screw on some machine, and as the screw gets turned and the machine gets adjusted, maybe that magnet moves closer to a sensor, and that can actually tell you the position of that adjustment. Just as an example, there's lots of different uses for Hall effect sensors. Okay, so now I want to talk about another type of Hall effect sensor. So this is the same idea as the linear Hall effect sensor I showed before, but this one behaves more like the reed switch. So basically, it's the same sensor, but inside the sensor, it actually has some extra circuitry that will basically measure the output and give you a high or low output. So we call that a comparator usually. And these are open collector output devices. If that doesn't make sense to you, check out my video on pull-up resistors, and that will explain what that means. So this does require a pull-up resistor of some kind on the output, which is, I'm using a 10 kilo ohm resistor. So now to complicate this further, there's two types of these digital Hall effect sensors. One is called unipolar, and one is called bipolar. So bipolar, let's talk about that one first because it's slightly more complicated. Bipolar sensors, basically you have to give a north or south pole to it in the right order. So let me demonstrate. So right now my multimeter is reading basically supply voltage, a little over 5 volts is the output for this. Now what I'm going to do is move my magnet close. Now notice nothing changed. This sensor has to be presented with the right face or the right pole in the right order. So I just flipped the sensor, and now you can see it basically goes to a low output. It's reading like, I don't know, 10 or 15 millivolts, so basically 0 volts. Now, if I bring that sensor back in, it doesn't change. Notice it doesn't change state when I take the magnet away. So basically this bipolar sensors have a latching effect. So once they've changed state, they won't change back until you present it with the opposite pole. So I just flip my magnet, put it back, and now it switched back to high voltage. So these, in my opinion, are a little less useful for the sorts of things I do. They're usually used for motor position. So usually a rotating magnet that has a north and south pole on it is what these are used for. So you can measure like motor RPM, things like that. But they are tricky because they have that latching effect and the state associated with them. Okay, so now here's the other type of digital Hall effect sensor. I just replaced the sensor with another type. This is a unipolar sensor. So these sensors are only respond to one, either a north or south pole. So let me demonstrate here. And they have no latching effects like the bipolar ones do, which is cool. So notice I'm putting the magnet close to the sensor and nothing's changing. It's still reading a high voltage. So if I flip the magnet end for end, now it switches. So notice now it's reading essentially 0 volts. Now if I take the sensor away, it flips back to high voltage. So these are unipolar. So these are still a little different than the reed switches, but pretty similar in that, you know, the output is one state without a magnet and another, and it's, you know, high voltage without a magnet present, and then a low voltage with the magnet present. But the difference with the reed switches is they pay attention to which pole of the magnet it's presented. So read the data sheet carefully to understand whether it's a north or south pole sensor, but they're real similar to reed switches in that way. Well, that's the end of magnetic sensors. The only thing I'll mention here is, I'm not going to get into them here, but they do have some more complex Hall effect sensors that can actually give you a 2-dimensional or even 3-dimensional position. So you can actually have a magnet in space near one of these sensors and actually get basically the direction and distance the magnet is away from the sensor. So those are used for much more advanced, like kind of position measurement applications. I'm not getting into any of those right here because I think the most useful ones are just these simple magnetic sensors, but do be aware that 2D and 3D Hall effect sensors do exist. Thanks for watching. Hope you learned something. See you later.